We've talked about acids, we've talked about bases. We're going to talk about polyprotic acids. And so polyprotic means that there's more than one hydrogen that can dissociate. And so we have multiple Kas because of the different hydrogens that dissociate. You'll notice on this slide that many of them have a double bonded oxygen with an OH group, and that's quite common for acids. It pulls the electrons away from the hydrogen, allowing it to dissociate. And depending on the number of acidic hydrogens, that's the number of Kas that we have. So if we have 2 hydrogens or diprotic acid, we have 2 Kas. If we have a triprotic acid, we have 3 Kas. You'll also notice that the first Ka is always larger than the second Ka. That first hydrogen dissociates easier than the second or third. Now, when we have the dissociation of a polyprotic acid, because that Ka is so much larger, we can think about it as a mixture of acids. Okay? So because our Ka is so much larger, the main contribution to our pH comes from the dissociation of that first hydrogen. But this is a sequential reaction. So as the first hydrogen dissociates and forms the anion, then that anion goes on to dissociate again to form, in this case, a -2 charge. And then if we look at the 2 hydrogen or H3O plus contributions, that first hydrogen or the first dissociation has a much larger contribution that, using significant figures, it makes up essentially all of the hydrogen that gets considered in our chemical reaction. All right, so here's a practice for you. We've got the dissociation of our first hydrogen from carbonic acid, the dissociation of the second hydrogen. Take a second, pause the video, and see if you can calculate what the pH of this solution is. All right, because we're still dealing with Kas, it is a weak acid, and so we are going to look at just the contribution from our first dissociation. We're going to write our ice table. Contains our carbonic acid, our hydrogen carbonate, and our H3O plus. So we have our initial concentration of our carbonic acid as 0.12 molar. When we first added, those are going to be 0. Our products are going to be 0. Our change is going to be -x because only one hydrogen is dissociating at a time. Our products are each going to be +x because there's a coefficient of 1 in our chemical reaction. All right, so we can look at our Ka expression, and in this case we're looking at Ka1, products over reactants. We're going to make the assumption that X is going to be small because our Ka is quite small compared to the initial concentration of the acid. And so we can substitute in our values. Again, we're assuming that x is small, so we're leaving that out of our equation. We're going to solve this, and x is going to be equal to the square root of our initial concentration times our Ka. And so in this case, x equals 2.27 times 10 to the negative fourth. And that would be molar. So that is the concentration of our H3O plus from our ice table. And so we can find pH by taking the negative log of this. And our pH is equal to 3.64. We're in the acidic range. And so we've already talked a bit about bond strength and how acidic our solutions are, because we've mentioned about how the attraction between the elements, between the hydrogen and our anion, if it's a strong acid, that means it breaks up nearly 100%. That means that the bond between the two has to be weak. If we have a weak acid, that means that the attraction between the hydrogen and the anion is much stronger. It doesn't want to break apart that nearly 100%. So if we look at our acids and the bond energies, you'll see that as the bond energies go down, the acids become stronger. Okay. This also has to do with electronegativity as well. Okay, because of the more that the electrons pull the bond, or the electrons are pulled away from the hydrogen, the stronger that acid is going to be. If we look at electronegativity here, we're comparing similar types of acids and looking at the electronegativity of the anion. And if we look at that, you can see how the more electronegative our elements become, the stronger that Ka value, or the larger that Ka value, the more that it's going to dissociate into the H plus and the anion. This happens with the number of oxygens as well. So as we add more and more oxygens, that is going to become more polar and pull the electrons away from the hydrogen, making it easier for that hydrogen to dissociate. So typically, the more oxygens that are included in our acid, the stronger it is. So here you can see the example with chlorine. So when we've got ClO4, it's a very strong acid, dissociates 100%. If we just have HClO, it has a smaller Ka value, so it isn't going to pull as many electrons away from that hydrogen. It's going to be a little harder to dissociate. We can also look at acid-base theory with a different definition. So this is the Lewis acid-base theory. So we've talked about Arrhenius acid-base theory. We've talked about Bronsted-Lowry acid-base theory. Lewis acid-base theory focuses on the electron pair. And so this tends to change, or this does change, the definition for the acid. So in a Lewis acid, it is a lone pair acceptor. So that's why positively charged things tend to be Lewis acids. Lewis bases are lone pair donors. So this is similar to what we saw in the Bronsted-Lowry definition, because nitrogen-containing compounds have an extra lone pair that can have the hydrogen bond to it. The difference with this definition is it does not require that positively charged species to be hydrogen. It could be things like what we saw in the lab in our pH of an indicator when we had the aluminum containing compound. We said that that was acidic, and that's because aluminum has a positive charge and can accept a lone pair. So when we do have Lewis base acid or Lewis acid base reactions, what happens is we form something called an adduct, okay, where we take the lone pair donating group and a lone pair accepting group, and they actually form a bond. And so these, an example of this is when we have water and carbon dioxide that form carbonic acid. We actually form a bond between that Lewis base, which is our water, and our Lewis acid, which is the carbon dioxide, and we get a new adduct that we call carbonic acid.